Hello and welcome back to Calculus 3, section 15.5 on directional derivatives and gradient. We talked about partial derivatives, and we only talked about partial derivative in respect to x and partial derivative in respect to y, which are the ones that measure the change at the given point only in the direction of x parallel to x-axis and the direction parallel to y-axis. So those were defined, and we were able to calculate a whole bunch of stuff, then did the chain rule for that. Now what happens if you want to measure the derivative in other directions other than just x or y, which are that I hat or j hat? So what if in the domain you want to go in a different direction? Well, there is a way to calculate the change, and it's really cool. It's just going to be the dot product between the vector of partial derivatives and the unit vector in a direction you want to go. So if you have some kind of a surface in x, y, z three-dimensional system, I can't really work on this one. How about, all right, let's try this, whatever. And you want to find the derivative at the point A, B, but the derivative is not going, see, A, B has its x direction and its blue y direction. So now, when you bring this point up and hit the surface, this point on the surface will be AB f of AB, because that's the output, right? F of AB, that will be a z component. So AB f of AB is on the surface of the, so now you're going to have a tangent line there, which is the red tangent line, and that tangent line is going to be the one that you get the slope from fx. Then you're going to have a blue tangent line, and that's your partial derivative in respect to y. But now, let's say purple, you want to go in a different direction, and this is some vector u. Well, in that case, you are going to have another tangent line here, whose derivative will be the directional derivative of f in respect to u. It says duff over there, but u is the subscript. Duff. Well, we can actually use the hat, because it's let's use a hat because it's the directional derivative. So what is this thing that we are learning? We are learning directional derivative at point AB in the direction of vector u. Now, vector u is in the xy plane. U is in xy plane, which is the domain. We need u hat, which is u divided by magnitude of u. So now, directional derivative in direction of vector u, and I'll put u hat of the function computed at AB, let's just do xy. In general, is going to be the vector of partial derivatives dotted with u hat. So this is your formula. Now I'll put also the exploded version at the point, but that's the formula. And then at point AB, our directional derivative at AB is going to be partial derivative computed at AB, comma, partial derivative of y computed at AB, dotted with the unit vector u1, u2. Find the directional vector at point 1, 3 for function. Thank you. I feel exquisite. In the direction of, and let's say you have a vector 1, 1. Well, you would take a look at the partial derivative, fx, and that would be derivative in respect to x, which is 6xy, which gives us that computed at 1, 3, you plug 1 and 3 in, is 18. Then we calculate partial derivative in respect to y, becomes 3x squared minus 3y squared. So fy at 1, 3 becomes 3 minus 27, which is negative 24. And here is the pitfall. I'll write it in blood. Vector 1, 1 is not a unit vector. Use u divided by u magnitude. 7 exclamation points right there. This is where your grade dies pretty much, every time. So yeah, 1, 1 looks cool, but it's not unit vector. So you have to, right? It's not a unit vector, so you have to find the unit vector. So u hat is going to be 1, 1 divided by root 2, which is 1 over root 2 and 1 over root 2. Yes, you can rationalize this to come up with root 2 over 2 and root 2 over 2. Now that is a unit vector. So now our directional derivative in the direction of u hat of the function computed at 1, 3 is going to be 18 and negative 24 dotted with root 2 over 2, root 2 over 2. So the directional derivative is equal to 18 divides by 2, so we get 9 root 2 plus 24 minus 24 is now 12, root 2 is negative 3 root 2. Now, this number here is the slope of the tangent line in the direction of vector 1, 1. So at 45 degrees. So if you look at the tangent line that is, so tangent line in the x direction will have the increase, and that increase is at the slope 18. The y direction has a decrease in a slope of negative 24. And then in the direction 1, 1, at the same point, you have a decrease, which is the slope of negative 3 root 2. Note that if you are standing at the point in the domain, right? Standing at a point in the domain, and right here is the point you're interested in, right? Now, look at this. I can go, this is the y direction, that's the x direction, because that's how we established, well, actually y direction would be this way, because that's 0, 0. So the way we established is, it will be, that's the x wall, right? Yes, that's the x wall. So if I am to stand, let's go stand at 0, 0, and bring the point. So now, what do we have? In our x direction was 18 increase, so it will go up at this point. Oh no, I'm next to point 1, 1. Well, I'm at roughly at 1, 1. So at 1, 1, you have the, that will be a 0 because it's flat, right? So 18 high up, that's a very high slope, going up. In a y direction, it will be going negative 24, going really down. And at the direction 1, 1 is, so between going really high up, which is a positive 18, and really going down at negative 24, you have a negative, whatever it was, negative 3 root 2. That's around almost 5.5 or whatever, right? It will be going negative. So at the point that you are computing, right, you will have these, and you can see that the slopes, right, going from here all the way here, all the way down. You see how the slopes are kind of creating the surface that it's falling as you go. So you can think about these things and make, depending on which in which directions you look at one point, you might be going uphill, you might be going downhill, you might be staying flat. On this surface of this desk, pretty much any point you stand at, it's flat, flat. But if you stand at the edge of this bottle right here, right? If I'm looking towards you, it's flat. If I'm looking towards the window, it's uphill. And if I'm looking towards the projector, it's downhill at the same point. So one point is going to have infinitely many slopes, depending in which direction you look. Because the direction of x-axis and direction of y-axis are your partial derivatives, and those are just two slopes that you can get, because now with the directional derivative, you have a vector that sits at a point and points in all possible directions, right? So infinitely many. And out of those infinity of directions you can look at, only two of them are x and a y direction for your regular partial derivatives, and the rest of the infinity of directions are covered by the directional derivative. So directional derivatives are extremely useful because we can quickly figure out the way to get the fastest way to go up or the fastest way to go down. And that's right, that's going to be, but before we do that, let's just define a part of this as a gradient. So just like a little subtitle over here, the gradient. This is just a definition, nothing special. So the gradient of f at xy is just the vector of partial derivatives. So fx comma fy. Now this is already the part of our calculation. This upside down triangle is called del. and you put, and clearly it's equal to a vector, right? So you will put the vector arrow on it. So del. Like computers. So now you can recast your duf into del f dot u. It's a nice compact equation to remember. Remembering vector equations, especially if they are working in any kind of dimension, is very useful, rather than memorizing the 2D case and then the 3D case, and you go to linear algebra and they say, well, in n-dimensional space, and you go, why? Well, because we can. So we have the vector equation here, and as you can see, this one is not dimensionally bound to either 2D or 3D or 4D. You can have any dimension you want. Just put enough variables. And now here is the theorem that we really want to know. This one is called directions of change. And it goes like this. So let f be differentiable at AB with the del FAB being different than 0 vector. Number 1. F has its max rate of increase at AB in the direction of the gradient at AB with the rate of change in this direction is the absolute value of del, which is the magnitude of the vector. So when you are on a surface and you want to find the steepest way up, you have the equation for the surface. You want to find the steepest way up, all you need to do is to find the partial derivatives, compute at the point you're standing at, and then calculate the magnitude of that vector. We know that absolute value on a vector means the magnitude. We know that del is just a collection of partial derivatives. Those partial derivatives will be computed at the point you're standing on, because that's the point xy, right, on the domain. So it's just, building blocks to understand what these things do. Now we're going to have exactly the same. We're just going to change maximum into minimum and put 2 negative signs. So in a direction of the negative, gradient is going to be the steepest descent, which is the fastest way down, the steepest way down. So what I'm going to do is I'm just going to copy this whole text and put those minus signs where they belong. So copy, paste, and I'm just going to put the negative signs in front of the gradient, and change max into a min. and increase into decrease. So f has its, x has its maximum rate of decrease, maximum rate of decrease, not the minimum rate of decrease, maximum rate of decrease. So f has its maximum ways. It's the fastest way up and the fastest way down. So max in both cases. Maximum up, maximum down. So the steepest way up and the steepest way down are the gradient, negative gradient, with these formulas that compute the value. And number 3, the directional derivative is 0. In any direction orthogonal to del FAB. That should be common sense because the dot product, right, would be 0. So if there is orthogonal between the vector and the gradient, then the dot product is 0, so directional derivative is 0. So now what are your problems? The problem says, here is the surface, they give you an equation, and they ask what's the fastest way up, fastest way down, and what are the, right, where we have zeros. So let's take a look at one of those. Then we're going to rewrite all of these equations. I don't know why, but we are into a 3D case, and that will be it for this lecture. Directions of steepest ascent and the steepest descent. Looking for something beautiful like 36. This is some, you're going to enjoy this. F of x, y is 2 sine. We want direction of steepest ascent and descent. Direction of steepest ascent and descent, i.e. fastest way up, fastest way down. We know we need to get partial derivatives. So I have derivative of sine is cosine. So 4 cosine 2x minus 3y. And fy is negative 6 cosine 2x minus 3y. So we have our partial derivatives, and the steepest, which is 4 cosine, and now when you plug in 0 it kills it, so it's negative 3 pi, comma, negative 6 cosine, negative 3 pi. So del f at 0 pi is going to be, now cosine is even function, so this minus sign doesn't count for anything, and at 3 pi is negative 1, so we have negative 4 and positive 6 when you compute. Again, when you draw the cosine, it starts at 1, dips down, dips up, that's where the 2 pi is, and then does the same thing one more time. This is where 3 pi is. So you see it's a negative 1 value for a cosine. So if it's a -1, cosine is -1 times 4, -4, -6 times -1 is +6. So this is our direction of steepest ascent. So if you're going in a direction of -4, 6, it will be the steepest way up from the point 0 pi where you're standing. And we can calculate the rate of that by simply figuring out the magnitude. So that's going to be square root of -4 squared plus 6 squared, which is, I don't need this cosine here, is 16 plus 36, which is square root of 52. Now, 52 we can factor out 4, it gives us 2 root 13. All right, so 2 root 13 would be the steepest way up. Now, steepest way down, which is steepest descent, it'll be very easy. You just put minus signs on everything, so you don't have to recompute. It's negative del f at 0 pi, which would be 4 -6 with a magnitude negative 0 pi, which is -2 root 13. So that will be the directional derivative. And now I'm just going to mention the formulas for the 3D, which are the same. So R3, we have directional derivative UF at ABC input to give us partial x, partial y, partial z, dotted with vector u. The third-dimensional gradient is exactly this creature here, fx, fy, and fz. You can also write this if you want as fx of x, y, z. I mean, if you're not lazy, you can just write out all of them like that. It's just too long. The R3 formulas just have an extra variable, and ascent, descent, and all of that stuff works exactly the same. These equations are not dimension sensitive. So we still have steepest descent with a del f ABC, with the slope m being absolute del f ABC, and steepest, there we go, descent negative del FABC with a slope negative del FABC. So R3 also has these. You can do R4, R20 if you want. It's all the same. That's the directional derivative. Calculate 2 partials, put them in the vector, or calculate 3 partials, put them in the vector, and dot that with the unit vector in a direction you want to take a look at the change. Now you might be a little bit wondering spatially for 3D right? Because it's easy on a surface, right? On a surface, you just say, yeah, I'm going downhill, I'm going uphill, right? What's happening? Why do we have this stuff? Well, you have to understand that when you have the R3 case, R3 is your input, that's your domain. So if the entire third-dimensional object which you hold in your hand is the domain, so what would be the range? The range could be the temperature. We talked about air conditioning dispensing cold air, and the temperature in the room is not everywhere the same. The coldest air is close to the vents. The hottest air should be by the window. Now, what I can do is I can pick a point in 3D space A, B, C, and the temperature is the fourth dimension value at this point. So now, if I'm looking in this direction, temperature might be going down. If I'm looking at this direction, temperature might be going up. No, actually down this way, up this way, because it's going closer to the window. So when you pick the point, and you make the direction in which you want to look, right, pretty much the temperature should be constant over here because there is a vent there, is a vent here. Right? These are important aspects of the design. You don't just put these things anywhere, right? They have to be calculated carefully using the volume of the room and everything else. Otherwise, you will end up with condensation in the vents, and then eventually mold, and then death. It's very, right? It's very simple. No, I'm serious. You have never heard of mold kills? See what people do because they don't know better. When the air conditioning thing dies in a right, which was designed for their house, they just go and buy a bigger one because their neighbor has a bigger one, so they're just going to buy a bigger one than their neighbor, right? And then they install that one. Well, guess what? If you put a double-size air conditioning, so you beat your neighbor, you better rip all of the ductwork in a house and put the new ductwork, because pushing that much air through the ductwork that you can't is going to condensate water, and the water will create mold, and the mold will create death. There we go. Very simple. Just like when those geniuses say, oh, the fuse keeps popping, so just replace the 15 fuse with a 20. Oh, it's not popping anymore. Great. 2 months later, no more house. You change a fuse, and the whole wire needs to change because the wire you have is rated 15 for the one. Temperature is proportional to electricity, which is the current. There is a very basic formula in physics. The more current, the more temperature, which means you need different wire to withstand that temperature. Anyway, so these are the things, or don't make houses of wood and cardboard. Where I come from, everything is concrete. You call the fire department, my bedroom is on fire. Just close the door and suffocate. That's it. That's what they say. Fire the truck for a room that it's on fire. No, I just close the door. That's all it takes. It's out. The walls, the concrete can't burn. That's it. Anyway, so that's the lecture on directional derivatives and the gradient. I want to take a few minutes break, and then when we come back, we are going to take a look at tangent planes and linear approximations and the differentials. A lot of cool stuff.